All right, let's dive right in. Today, we are going to get into a really powerful technique in survey sampling called regression estimation. If you've ever found yourself looking at a simple sample mean and thinking there has to be a way to make this more precise without just dumping more money into a bigger sample size, well, this is for you. We're going to see how using a little bit of extra information can completely change the game for our estimates. So here's the plan. First, we're going to lay out the basic problem we're trying to solve. Then, we'll talk about the key insight that opens the door to a better solution, which is all about using auxiliary data. From there, we'll actually build the regression estimator piece by piece. After that, we'll do our due diligence and check its properties, things like bias and precision. Then, to make it all real, we'll walk through a case study about counting dead trees. And finally, we'll see the payoff and just how much better our estimate can get. Okay, so let's start at the beginning. What's the fundamental challenge here? When we take a sample from a population, our whole goal is to estimate something, like the population mean. And we want to be as accurate as possible with as little variance as we can get. The real question is, what's the best tool for that job? Which brings us to this big question. Our go-to, our standard workhorse, is the sample mean, right? We call it Y-bar. It's a great, unbiased estimate for the true population mean, which we're calling Y bar U. It's our starting point, but, and this is the key, is it the absolute best we can do? Is it the most precise? Does it have the smallest possible variance? Or is there another estimator out there that can consistently get us closer to the true value? The answer, as you've probably guessed, is a huge yes. So, how do we get that extra precision? Well, the secret isn't in the main data we're trying to collect. The key is in other related information that we might already have. This is what we call auxiliary information, and it's a total game changer. Just take a look at this slide. It perfectly shows what we're talking about. You can see a really clear linear relationship between age on the x-axis and muscle mass on the y-axis. If you know someone's age, you can make a much better guess about their muscle mass than if you knew nothing at all. And that's the whole insight in a nutshell. If our variable of interest, our y, is correlated with some other variable, an x, and we have more info about that x, we can use that relationship to sharpen our estimate of y. Now we need to formalize that idea with a model. We're going to assume that the relationship can be boiled down to a simple straight line. The formula you see here, E of y equals b0 plus b1x, is just saying that the average value of our target variable y is a linear function of our auxiliary variable x. b0 is just the intercept, where the line hits the y-axis, and b1 is the slope, which tells us how much y changes for every 1 unit change in x. This simple linear assumption is the foundation for everything we're about to build. Okay, so we've got the insight, we've got the model. How do we turn that into a real practical tool we can actually use? Let's build the regression estimator. First up, we need to estimate the parameters for our line, the slope b1 and the intercept b0, using just our sample data. And what you see here are the standard formulas from ordinary least squares. Our estimate for the slope, which we call b hat 1, is just the sample correlation, r, times the ratio of the sample standard deviations. And our intercept estimate, b hat 0, is set up specifically to make sure our estimated line goes right through the center of our data, the point x bar, y bar. And here it is. This is the tool we've been building up to, the regression estimator, y hat reg. Just look at how it's built. It starts with y bar, our simple sample mean, which is our basic first guess. But then it adds a correction term. That correction is our estimated slope, b hat 1, multiplied by a really interesting difference, the true population mean of x, x bar u, minus the sample mean of x, x bar. And having that true population mean for x, that's the piece of auxiliary information that makes this whole thing work. Let's really break down the logic of that adjustment. We start with our plain old y bar, then we look at that term in the parentheses, x bar minus x bar. Think of this as a reality check. It tells us if our random sample just happened to be a little weird with respect to x. For example, let's say our sample mean x bar is lower than the true population mean x bar u, and we know x and y have a positive correlation, so b hat 1 is positive. Well, that suggests our y bar is probably too low as well. So the formula takes that positive error, multiplies it by the positive slope, and adds a positive correction, nudging our estimate up to where it should be. It's literally using our knowledge of the whole population of x to fix the random sampling error in our one little sample. It's brilliant. Okay, so we've built this new tool. But before we start using it, we have to do our due diligence as statisticians. How good is it really? Is it biased? How much more precise is it? Let's dig into the properties of this estimator. Now, here's a crucial point you need to know. Unlike the simple sample mean, the regression estimator is technically biased. The math shows that the bias is equal to the negative covariance between b hat 1 and x bar. This happens because both of those values are calculated from the very same sample, so they aren't independent. But, and this is a really big but, for large simple random samples, this covariance gets incredibly close to zero. The bias pretty much vanishes. So in practice, we usually treat the estimator as being approximately unbiased and don't lose any sleep over it. So what about precision? For that, we look at the mean squared error, or MSE. Since the bias is basically zero for large samples, the MSE is pretty much just the variance. Now let's look at this formula. The MSE is approximately our old friend, the finite population correction, 1 minus n over n, times s squared over n. The new player here is s squared d. This is the population variance of the residuals. Think of it as the variability in y that's left over after we account for the linear relationship with x. It's the noise the regression line can't explain. But check this out. This second equivalent formula for the MSE is where the magic really becomes obvious. It rewrites the MSE using s squared y, which is the total variance of y, and r, the population correlation between x and y. Now zero in all that last term, 1 minus r squared. If x and y have zero correlation, r is 0, r squared is 0, and that term is just 1. Our MSE is basically the same as it would be for a simple sample mean. But as that correlation gets stronger, as r gets closer to positive or negative 1, r squared shoots up towards 1. That makes the whole 1 minus r squared term shrink towards 0, and our MSE plummets. That is the secret sauce. A strong correlation means a massive gain in precision. So this table really sums it all up. How do we get a super precise estimate? Well, a bigger sample size n always helps, that's nothing new. It also helps if our target variable y just doesn't vary that much to begin with. But the real game changer, the new lever we get to pull with this technique, is that correlation, r. Finding an auxiliary variable x that is strongly correlated with our target variable y is the single most important factor for making this whole method pay off. All right, enough with the theory. Let's make this concrete and see how it works in the real world. We're going to use a classic example about estimating the number of dead trees in a forest. Okay, here's the scenario. Our population is a forest area divided into 100 plots. We can fly a drone over all 100 plots and get a quick, cheap, but not perfectly accurate count of dead trees from the photos. That's our auxiliary variable, x. And because we did this for every single plot, we know the true population mean of these photo counts. It's x bar u equals 11.3. Now, to get the real, accurate count, our target variable y, we have to send a crew out to walk the ground, which is time-consuming and expensive. So we only do that for a random sample of 25 plots. So from that sample of 25 plots, we crunch the numbers. We find that the sample mean for our quick photo counts, x bar, is 10.6. And right away, we notice something. Our sample mean of 10.6 is a bit lower than the true population mean of 11.3 we already know. It seems our random sample, just by chance, happened to pick plots with slightly fewer dead trees in the photos. Meanwhile, the accurate field count mean, y bar, is 11.56, and we see a decent positive correlation between the photo counts and the field counts of about 0.62. Now we just plug it all into the formula. We start with our simple mean, 11.56. We add our estimated slope, which works out to be 0.613, and we multiply that by the error term, the true mean, 11.3, minus our sample mean, 10.6. That difference is a positive 0.7. And see what happens? Because our sample's photo count was a little low, and we know the two counts are positively related, our estimator does exactly what it's supposed to do. It adjusts our final estimate upwards from 11.56 to a more accurate 11.99 dead trees per plot. So after all that, was it actually worth it? We brought in this auxiliary variable, we ran a regression, we adjusted our estimate. Let's look at the numbers and see what the real payoff was. This right here is the bottom line. This is why we do it. The standard error for our original estimate, the simple sample mean, was 0.522. But the standard error for our new, smarter regression estimator is just 0.408. That is a really nice reduction. A smaller standard error means our estimate is more precise. It means our confidence intervals are going to be tighter. We're more certain about the true value. And we achieved all of this without having to survey a single extra plot in the field. That's the power we're talking about. And of course, to get our estimate for the total number of dead trees in the entire forest, we just scale up our mean. We take our estimated mean of 11.99 trees per plot, multiply it by the 100 plots in our population, and we get a final estimate of 1,199 dead trees. And just like we scale up the estimate, we can scale up the standard error. We multiply the standard error of the mean, that 0.408, by the population size of 100. That gives us a standard error for the total of 40.8. And this is the number we'd use to build a confidence interval around our total estimate of 1199, telling us just how certain we are. So we'll end with this question, which really brings it all home. If you're designing a survey and you could pick the perfect auxiliary variable, what would you look for? Well, based on everything we've seen, there are two non-negotiables. First, you have to know its population mean, x bar u, or it has to be super cheap to find out for the whole population. And second, it needs to have the strongest possible linear correlation with your target variable y. It doesn't matter if it's positive or negative, just strong. You get those two things, and you've got the key to unlocking some serious gains in statistical precision.